Okay, some of you are still confused. Why doesn't it fall down? In fact, it is falling down. Just forget about the circular motion, forget about this circular road, etc. Just imagine projectile motion. Now, we have already studied the projectile motion. If you take a mass, throw it upward, it will just follow a parabola. Well, you don't have to just take this object and throw it vertically upward. You can just throw it horizontally. You can throw it horizontally. So this is the trajectory. The trajectory is almost horizontal. But of course there is the acceleration which is accelerating it downward. The force is only downward. But nevertheless the object doesn't fall immediately. It falls in time. During this time the object is moving horizontally also at the same time. Because although the force will only change the velocity. That's it. That's the only thing the force does. It has an initial velocity. There is a force downward, so it will be accelerating downward. Now, if I take this ball, and if I want it, now in this example, when I throw it to your friend, you just follow such a trajectory. Now, if I want the ball to go not like that, but rather just follow this circle. Now, we know that under the influence of gravity only, it will not be able to follow this parabola. It will go too far. So what should I do is I have to somehow change its direction faster than the gravity would change it. That means I have to exert an additional force pushing it downward so that it will follow this small circle. Rather than flying away like that, it will just go down almost immediately. That means I have to exert another force, and that is why we have this normal force pointing downward at that instant, if it is going very fast. Okay, the gravity will change the direction of the velocity downward, but if that is not enough, I need another force. Otherwise, it will just go through the wall, through the road, the circular road. And if the road will not allow it to go through it, so it will just push it out or push it downward. This one, well, these were your claims. Now, these were just what you said. Now, my explanation is this one, this orange one. So, if the speed is fast, I have to exert a normal force in the downward direction. Normal force is always perpendicular to the surface creating the force. So, in this case, I'm just right at the top of this circle, and that surface is exerting the normal force, so it can only be downward. So if it is going very fast, the normal force has to push it further down. Gravity is already pushing it down. The normal force has to push it down. As the speed gets smaller, well, the trajectory in the absence of the road, the parabola will almost follow this circular road already. So already it will be, if I just throw it with a smaller velocity, it is already almost following the circle. So I just need to make a very small correction to this motion only under the influence of gravity. I have to just push it very slightly. So the normal force will be smaller. And there will come a point, if I keep reducing the speed, there will come a point at which the velocity, the normal force will be equal to zero. At that instant, what is actually happening is that the parabola and the circle, at that point, they overlap. So already the object, for a very small amount of time, is following the circle or the parabola. Because for a very small amount for a very short segment, a parabola and the circle will be the same. So I don't need to exert an extra force. So at that instant, the normal force will be zero. Now, if I throw it with a smaller velocity, well, the parabola is now narrower than the circle. That means it's just falling down. So at the instant when the normal force becomes zero, for the value of the velocity, of the speed v that the normal force becomes 0, my ball is about to fall down. So if it is to go around the circle, normal force has to be greater than 0. The minimum value is 0. No, the speed is never 0. You see, the speed, since the horizontal component of the speed is never 0, it will go horizontally. But if the speed is smaller than the value that we had evaluated here, if the speed is smaller than this value, then what will happen is, okay, if this is my circle, let's say, I throw it, well, it just loses contact immediately. So it will not follow this circle anymore. But of course, if there is a horizontal velocity, then it will follow this parabola, not the circle.
When you were explaining this, the example was that of the motorbike negotiating that curve, right? My question is, for example, I think that it also depends, everything also depends on the angle the bike makes with the original.
Well, you see, we started with understanding what's happening in the motorcycle example. Okay. Now, one thing we do in physics almost all the time is simplify the problem. The simplest example, the simplest problem that you can think of, which is similar to the motorcycle example, will be just a point object. Okay. This is our motorcycle. Of course, for a real motorcycle, there will be much more complications. There will be the engine running. There will be rotations of the motorcycle itself, the rotations of the wheels. It will complicate the problem further. But it will not really change our understanding of what's going on. If you are actual motorcyclists trying to do this trick, I mean, you wouldn't just take this calculation. To be on the safe side, you will probably either do a more precise calculation, or you will try to make sure that your speed is something like double this limit value. This is just a simplistic model of what is actually happening in the motorcycle case. Now, other questions on this example?
What if it was reversed? What if instead of the object going like upside down, it went over a hill and we wanted to prevent it from sliding off the hill?
Flying off the hill, okay. Let's do the same example. So this is the question. So you have a hill, and you have your object moving upward. And at some point it will come here with some speed v. Now I'm sure you have experienced it, especially if you are taking the dolmushes quite frequently, you will feel it. So there are all these bumps on the road, especially on campus, so they are just mainly like this. You have your bumps. This mass over here, you can just think it's the wheel of the bus, or you can even model the bus itself as just a small dot. If the dolmush is going very fast, you will just jump in your seat. The dolmush will jump. It will lose contact with the road. If it goes slowly, you will not have that limit. Now, the difference between this one and the previous problem is that in the previous one, if it is going slowly, then it will fall down. It will lose contact. In this one, if it is going faster, it will lose contact. So you can ask, what is the minimum speed such that the mass doesn't lose contact at the top? What is it? What is the, yes, the maximum. So if your speed is larger than that, you will lose contact. The problem is in fact identical. Even the solution is identical. Again, you see, in this case, we need a normal force which will be pointing outward. And again, if you want to compare with a projectile motion, if the speed is very small, let's say at this instant, it's moving uphill. If the speed is small, and if there was no hill, then this projectile will just follow such a trajectory. It will try to go into the surface. But the surface wouldn't allow it. What I mean by not allowing it will just push it outward. So that's why we have a normal force if V is small. So there will be a normal force. And here there will be also a normal force. We have the weight and the normal force. So if this is the x direction, we can write the normal force as n in the x direction. The weight will be mg in the minus x direction. The total force will be n minus mg in the minus x direction. And if at that instant we assume that it's making a circular motion with radius r, this should be equal to mv squared over r in the minus x direction. Again, at this instant it's making a circular motion. This r is the radius of the circle. V is the speed at that time. And so if you solve for the normal force becomes mg minus mv squared over r. This is n. And for our object not to lose contact, this n has to be greater than or equal to 0. And that gives you the maximum speed. Oh, you're right. So let's see. This is plus x. So we have n minus mg should be equal to minus mv squared over r if everything is correct, and n is equal to mg minus mv squared over r. And this should be larger than or equal to 0. And this inequality gives you the maximum value of v. If the object is not to lose contact. But the idea is exactly the same. You say, first of all, what does the lose contact mean? Well, lose contact, it just means the normal force becomes 0. After that point, it will just lose its contact. Then we just write the Newton's second law. We identify the forces. We can draw a free body diagram, identify the forces, calculate the total force. Well, if it is doing some circular motion, then we know that the central acceleration has to be v squared over r. There can be some other tangential acceleration which we might not know. We will be calculating it later on, but not now. At that instant, at least, the force is in the central direction. The central acceleration is v squared over r. So this is nothing but, this is the total force. This equality is the Newton's second law. And from this equality, if we solve this equation, we have these two vectors that are equal. So their components have to be equal. N minus mg should be equal to minus mv squared over r. The normal force when my object is at the top is given by this expression. And losing contact, not losing contact, let's say, just means that the normal force is larger than 0. Any other questions on this one?
So
the question is, what is the maximum velocity that it doesn't lose the contact. If my question is, what is the minimum velocity that can enter the object or SA2? That's really good question.
Well, you see, those type of questions we will study. So your question, if I understood it correctly, you just send an object with some initial speed, and then of course there will be some tangential acceleration. It will slow down as it's going upward. And what is the minimum speed that it should have such that it will be able to go to the top, right? Those kind of questions we will study next week.
Well, my question is that in a diagram, if you have, let's assume based on what we're talking about, you said if it should lose contact, then n should be greater than or equal to 0. But
If we are not to lose contact, then n should be true.
now, that if you draw that you have a circle and you have the ball as you, for example, on that it maintains its path on that circle, you realize that I don't know if I should draw a diagram, probably should explain myself because I need to draw a diagram to explain myself.
Okay, in that case we can discuss it after the class. Now, any other questions on this one?
Can we lose contact and then again?
Of course, I mean, depends on the shape and depends on your speed. So you can just this shape can have such a shape. Let's say if you lose contact, what will happen is it will just lose contact and then fall down. I mean, it depends on the shape. Is it a circle, or does it just look like a circle? I mean, you have to follow the trajectory of the object and then see if it falls down or not. I mean, if you are watching Hollywood movies, you have all these scenes of car racing down the hill, and the car just loses contact and just lands on the road. So, depending on the shape, it will of course gain contact. But if there's a cliff over there, you will lose contact. You fall down the cliff, and you will never fall onto the road. Okay, let's look at another example. It is called the conical pendulum. Some of you are asking what happens if there's gravity. So that's basically what we will be studying now. So we have this object. So this, we will be studying the circular motion. It just follows a circle. There is the gravity. What are the other forces? So this point is fixed. Here is my mass. It is going around the circle. Let's say speed is v. Now let's first, whenever you are dealing with such problems, you always first draw a free body diagram. So what are the forces acting on this one? There's a tension. What else? There's also the weight. Any other force? Centripetal force? No. It doesn't exist as a separate force. Other forces should sum up to give us the centripetal force. Well, first let's choose our coordinate axis. Let's just choose them to be x and y. And first let's write our forces in terms of their components. Now the tension force, so it has, let's say this angle over here is theta. So if that angle is theta, this angle over here is also theta. So the tension force is T sine theta in the -x direction and T cosine theta in the y direction. This is the force due to the tension on the string. Now the weight is just mg in the minus y direction. So we just need to calculate the total force. Now the total force is equal to t sine theta in the minus x direction plus t cosine theta minus mg in the y direction. What is the direction of the acceleration of this object at this instant? It should be in the minus x direction. We said that it is doing some uniform circular motion. It's doing uniform circular motion. Well, of course, the center of the circle is some point over here. It's always towards the center. Now, at this instant, towards the center just means the minus x direction. So the acceleration vector at this instant is in the minus x direction. What's its magnitude? It's v squared over r. This is r, v squared over r. So this is our acceleration vector. Now we have this is the total force. This is the acceleration of the object. And Newton's second law just tells me that these two are related. This is the total force. And Newton's second law tells me that this should be equal to mv squared over r in the minus x direction. Now, first of all, what is the component of the force in the y direction? It should be 0. Acceleration doesn't have a component in the y direction. So the total force shouldn't have any component in the y direction. This has to be 0. T cosine theta minus mg should be equal to 0. Well, tension is something we didn't know. So this tells me that tension has to be equal to mg over cosine theta. Now, secondly, the x component of the total force is just t sine theta minus t sine theta. And this should be equal to the x component of this vector over here, which is minus mv squared over r. We already know what t is, at least in terms of this angle theta. T sine theta is nothing but mg tangent theta should be equal to mv squared over r. And this just tells us that m's we can cancel. V squared should be equal to g times r times tangent theta. Now, at least this allows us, you see, in a practical way, it's easy to measure the angle theta. You just take a video of the conical pendulum, and that video will tell you what theta is. From the video, you can just measure the angles. You can measure the distances, and that will tell you the angle. So you can easily determine the angle by just taking a video without touching your pendulum. And this would allow you to calculate what the v is, what the speed is. Any questions on this one? Okay, I repeat, there is no centrifugal force. In the free body diagrams, there is no centripetal force or centrifugal force. The other force, the forces acting on my system, they should sum up to give a centripetal force, pointing towards the center. There is no force acting on my mass away from the center. The net force has to be always towards the center.
Could you repeat y minus its acceleration direction?
You see, this object is doing circular motion. Okay. I'm looking at it at this at this instant. No, at this instant. This is my x direction. The center of the circular motion is this one. Well, since it's uniform circular motion, there's only a central acceleration towards the center. In this case, at this instant, it is the minus x direction. Of course, when my object moves over here, let's say, the acceleration will not be in the minus x direction, it will be in this direction. It will change in time. But the Newton's laws have to be valid at every instant. Any other questions?
Burada v kare dr tanımına eşitledik ya. Bu mesela eğik bir düzlemde sürtünmesi diyelim. Aracın şöyle yan gittiğini farz edelim. Orada da mesela aracın yoldan çıkmaması için gerekli bir neden yaşamalı diyebilir miyiz?
Let's see. Let's assume you are driving a car and you go around the curve. We will ignore friction this time, but we will assume that okay, your car is going around the curve, assuming it's moving at constant speed. Let's say the radius of the curve is r, but the road is not flat, is not horizontal. The road has such a shape. So this is your car. This is the car. And this angle over here is theta. Let's ignore friction. There is no friction. Now, if there is no friction, the car will not be able to take the curve because there is no force acting on the car. If there is no friction, then there is no force acting on the car. It cannot change its speed, its velocity. The velocity will be constant. It cannot accelerate. It cannot it cannot increase its speed. It cannot lower its speed. It cannot go around curves if there is no acceleration, unless the curve is banked like this. So what is the relation between theta, v, and r? If the car is to go around this curve. Now you see, in this curve, the car is doing some circular motion. And we know that if the car is to do some circular motion, then there has to be some central acceleration. And the central acceleration is v squared over r. So there is a central force, which should be mv squared over r. So there has to be a central acceleration, central force. Now what are the forces acting on my object, on my car? So this is my car, there is the weight. And there is the normal force. This is the normal force. And this is the radial direction. Let's call it the x direction. This is the y direction. Now the acceleration of my object, the central acceleration, is v squared over r in the x direction. This is the x. This is the y. Why the acceleration is in the x direction? Because at this instant, x is pointing towards the center. And we do the same things. We just identify the components. The normal force, well, let's first identify some of the angles. Now, if this angle over here is theta, this angle will also be theta. So the normal force makes an angle theta with the y-axis. So the normal force vector, in terms of its components, is just n sine theta in the x direction plus n cosine theta in the y direction. We have the weight, which is mg in the minus y direction. And the total force is just n sine theta in the x direction plus n cosine theta minus mg in the y direction. So this is the total force acting on my object. Now I use the Newton's second law. I write the Newton's second law for this system. And Newton's second law tells me that this should be equal to mv squared over r in the x direction. So this one over here, v squared over r in the x direction, is nothing but my acceleration. Of course, I am assuming that it's not changing its speed as it's taking the curve. So there's no tangential acceleration. The only acceleration that exists is the central acceleration. And then the next thing, you just equate the components of the vectors on both sides of this equation. So on one hand, we have n cosine theta minus mg. This should be equal to 0. On the other hand, we have n sine theta is equal to mv squared over r. This is the y component, the equality of the y components. This is the equality of the x components. And again, you can calculate n, you can calculate theta, etc. Whatever you want. The previous one.
I thought that n was upwards like that.
No, n is perpendicular to the surface. Well, of course, for a car that goes around this curve and for a car going on the other side of the road, the radius will be different. Now, we can also ask the question, what happens if, let's say, theta is smaller? Just by looking at this graph. If theta is smaller, what will happen will be the n vector will become more vertical. If the normal force is more vertical, it means that there is a smaller force in the horizontal direction. There is a smaller central force. Well, if there is a smaller central force, either you have to lower your speed or increase the radius. Well, increasing the radius would just mean that you will be going around a larger circle, so you will get out of this road if theta is smaller than the value we obtain with this speed. Or if you take for a given theta, you see the normal force, let's see, for a given theta, the normal force is mg over cosine theta. Okay, by the way, if you note here, the normal force is not equal to the weight. It is larger than the weight. Because this cosine theta is a number smaller than or equal to 1, so the normal force is larger than the weight of my object, the magnitude of the normal force. I mean, sometimes you get confused that the normal force is always equal to the weight. Here's an example where it's larger. So once theta is fixed, the normal force is fixed. So if the normal force is fixed, theta is fixed, this side is fixed for a given system, for a given road. So if you increase your speed, remember, for a given road, n times sine theta will be fixed for you. So if you increase your speed, you should also increase the r. That is, you are going around a larger circle, but that means you are getting out of the road toward the left. If you lower your speed, then you also have to lower r so that v squared over r is smaller. But if you lower r, that means you are turning really fast. So let's see. So this is our curve. So this is the trajectory that you would follow for a given speed. Let's call it v critical, this critical speed. Now if you go with a slower speed, If you go with a slower speed, remember, whatever your speed is, n is determined by your weight and by the road itself. N doesn't change if you change your speed. So n sine theta doesn't change if you change your speed. So mv squared over r shouldn't change if you change your speed. If v gets smaller, r should also get smaller. So you are going around a smaller circle. This is for vs smaller, if you go with a smaller speed. If you go with a larger speed, if v is larger, r will also become large. If r gets larger, then this will be your trajectory. V larger. In both cases, you get out of the road, since there is no friction. Now let's discuss one more thing. In real life, of course, there is friction, and you rarely go around banked curves. If you take in a bus, all the curves in, let's say, on campus, they're just horizontal. So what creates the center of force? The normal force will be vertical. It won't have any component in the central direction. So what creates the center of force? Friction or any other ideas? The normal force is vertical. It's not pointing towards the center. No. The normal force is always perpendicular to the surface. The surface is horizontal. Normal force is always perpendicular. Friction will be proportional to the normal force. You see, be careful about the applications of the third law, because these action-reaction pairs are acting on different objects. And the acceleration of an object is determined only by the forces acting on the object. So in this action-reaction pairs, only one of them is relevant for you, not the other one.
When the driver turns the wheel, the system of the automobile turns the wheel as well.
Okay.
So there's a force that causes change direction.
Of the wheels, yes, but why does the changing of the direction of, but that is a force acting on the wheels. What causes the change of the direction of the car? That's what we call an internal force, what we are mentioning. What's the external force acting on the car that causes the car to turn around? It's the friction. In all cases, it's the friction. If there is ice, the friction will be lowered and you will not be able to go around the curves. What kind of friction? Static or kinetic? Static or kinetic? It is static, because you see the distinction, what makes the difference between static friction and kinetic friction is not the motion of the object as a whole. It's only the relative motion of the surfaces. And unless your wheels are slipping on the road, the relevant friction is the static friction, not the kinetic one. Any last minute questions? Okay, in that case, see you on Saturday.